Minasan, konnichiwa. Zamurai Engineer desu. In this video, let us continue with the computation, actual calculation work. But this time, compared with the previous module, which is forward, we are now going to implement backward divided difference. So backward divided difference approximation method is defined as this. We have the same result if we are using calculus, but if we are using a finite value of delta x, you will notice that the delta x here is actually negative. The delta x is negative. That's why, as you can see on the numerator, the slope or the first derivative is actually function of x minus function of x minus delta x. So you will see the minus delta x. So meaning to say, there are 2 points relevant to our discussion, one of which is x and the other is x minus delta x, which is supposedly, if you compare the value, x is of a larger magnitude than x minus delta x. So let us approximate using numerical methods with finite value of delta x. Our first derivative of function of x is equal to the numerator function of x minus function of x minus delta x divided by the denominator delta x. So as you can see, just like what I said, our diagram shows there are 2 points, one of which corresponds to x and the other is x minus delta x. Okay, so therefore we can use this also to an example, and our example is the same as previous ones, and actually we already presented this example. The velocity of a rocket is given by velocity function of t is equal to 2000 natural log of quantity 14 times 10 to the 4th power divided by 14 times 10 to the 4th power minus 2100 t minus 9.8 t, wherein t has a valid region from 0 to 30, including both 0 and 30. When v is given in meter per second and t is given in seconds, use backward difference approximation method of the first derivative of the function of the v function of t to calculate the acceleration at t is equal to 16 seconds. Use a step size of delta t is equal to 2s. So it is the same. You can recall. Let us find this out by recalling our previous sample regarding backward difference approximation or BDD. So if that is the case and the velocity function is given, we can find a function for acceleration. Due to the relationship with velocity and acceleration, we could have a numerator v function of t minus v function of t I minus 1 divided by the denominator delta t, while t at I is equal to 16 seconds. So let us solve for the unknowns So delta t is given as 2 seconds. So therefore, if the time at ti is equal to 16, therefore at time at ti minus delta t is 16 minus 2, which is 14 seconds. So we have the 2 points, 16 and 14. So let us evaluate the velocity at each of these points. So velocity at 16, this is how you can calculate it using the given function, and also the velocity at time 14 is on the lower line, okay, which is equal to 334. So this is how you have to do it. Just substitute the value of 14 to the variable t. Okay, so we have all the needed information. Therefore, we can solve for acceleration at 16 seconds. So if we do that, we can find out the acceleration at 16 seconds is equal to 28.915. This is the value if we are looking at backward divided difference. Okay? However, let us take note from our previous example, or by taking the derivative, we can find that the actual or the true value of acceleration at time 16 is actually 29.674. 29.674. And our approximation is what? 28.9. So it is very near, okay? Less than 1 meter per second, okay? Difference. So therefore, we can find out that the absolute relative true error is actually equal to 2.557, which is better. This is a better approximation than forward divided difference method. Okay, we calculated and solved the resulting calculation gives us the absolute relative error using forward is 2.7%, while we have what? 2.6%. 2.6% is better than 2.7 if we are talking of errors. We want errors to be lesser, okay? But they are almost equal. Okay. Now, let us go to the next goal of this module. Okay, effect of step size. So, what is our concern here? We would like to have an example, other than the previous example, which we can play with the x variable. X variable is actually our delta x. So let us play with the value of x and try to observe what will happen if we change the value of x. So we will do that on our next video. And thank you for your time listening to us. Again, this is Dr. EYPEI, preaching engineering for nation building.